Since 4000 BC, wind energy has been utilized to power sailboats, grind grain, and pump water for irrigation fields, and more recently, electrical generation. According to science.jrock.org, during the 500 to 900 AD, the Persians developed windmills to crush grain and pump water. Until the late 1100s, the English developed windmills to crush grain. When the 1300s came, the Dutch developed windmills to drain water from low-lying areas. Here comes the 1800s. During the 1887, it is believed that Professor James Blythe made this groundbreaking discovery during this time. After just 1 year, on 1888, Charles Rush builds the first electricity generating windmill in Cleveland, Ohio, to provide electricity for his mansion, which later on was bought by a company called General Electric. In the 1990s and 2000s, the US federal government established incentives to use renewable energy sources in response to a renewed concern for the environment. Ever since, wind energy has been utilized mainly to generate electricity with the use of wind turbines, and the demand has been growing due to the decrease of supply in fossil fuels and its increase in price. Wind power is one of the world's fastest growing energy sources. As of the end of 2017, the world's total wind energy capacity had climbed to 539 gigawatts, thanks to new installations around the world. If you would rank countries with highest wind power capacity, China is the world's number one with a whopping wind power capacity of 188 gigawatts. The United States comes second with a capacity of 89 gigawatts. Germany, India, and Spain follow this list. Despite the fact that wind is free and renewable, it has its own disadvantages. First disadvantage is that current wind turbines are expensive and they generate power only when the wind blows, making their output inherently unreliable. Furthermore, wind turbines must be located where the wind blows, which can be far from traditional power systems, necessitating the construction of new high voltage power lines. Nonetheless, wind turbines are likely to play an ever-increasing role in global energy supply soon. Now, let's go ahead and talk about wind turbine types. Wind turbine types are categorized according to the rotation of their axis of rotations. These types are horizontal axis turbines and vertical axis turbines. Horizontal axis turbines consist of various designs. Vast majority of wind turbines being built around the world are of this type. They are often built in clusters referred to as wind farms. Horizontal axis examples of their turbines are single-bladed, double-bladed, three-bladed, US farm windmill multi-bladed, bicycle multi-bladed, upwind, downwind, multi-rotor, and field underrow, sail wing, counter-rotating blades, crosswind subvenues, crosswind paddles, diffuser, concentrator, unconfined vertex. For vertical axis turbines, it consists of four different main designs. These four designs are primarily drag type, primarily lift type, combinations, and others. Every, every wind turbine has a distinct power performance curve. One example is shown below, which plots electrical power generation as a function of wind speed V at the turbine's axis height. There are three significant locations on the wind speed scale. First, the current speed is the lowest speed at which useful power can be generated. The rated wind speed is the speed at which the rated power is delivered, which is usually the maximum power. The cutout speed is the maximum wind speed at which a wind turbine is designed to produce power. At wind speeds greater than the cutout speed, the turbine blades are stopped by some type of braking system to avoid damage and for safety reasons.
Wind turbine efficiency. An actual wind turbine can produce only a percentage of available power potential into actual shaft power, and this percentage is called the wind turbine efficiency. And this is determined from the formula wind turbine efficiency is equals to shaft power over available power. The available power can also express as wind power potential formula, whereas it is 1/2 times density times wind area and times the cube of wind velocity. Next, we can solve the electrical power output using the formula electrical power is equals to gearbox or generator efficiency multiplied by shaft power. Here, the shaft power refers to rotor shaft power output. A gearbox or generator connected to the turbine converts shaft power into electrical power output. The gearbox or generator efficiency has typically have an efficiency of 80% above. Overall wind turbine efficiency can also be defined as the electrical power output divided by the available wind power expressed in this formula. Note that a given wind turbine efficiency sometimes refers to overall wind turbine efficiency. The overall wind turbine efficiency is related to wind turbine by this formula. Overall wind turbine efficiency is equals to wind turbine multiplied by gearbox or generator efficiency. Whereas wind turbine efficiency is equals to shaft power over available power and the gearbox or generator efficiency is from the equation of electrical power output. If we rearrange them, we can get electric power over shaft power. We both cancel the shaft power and now we will get electric power over available power. The efficiency of wind turbine is usually referred to as power coefficient or C sub P. Using the formula of wind turbine efficiency, we can get the actual shaft power output from a wind turbine as shaft power is equals to 1/2 times the wind turbine efficiency times density times wind area and times the cube of wind velocity. The efficiency of wind turbines usually ranges between 30 and 40%. Now look at the figure. The figure shows the flow of air across a wind turbine. If we neglect frictional effects in a wind turbine and take the wind velocity as the average velocity of air at the turbine inlet, we can state that the portion of incoming kinetic energy, which is the mv sub 1, does not converted into electric power will leaves the wind turbine as an outgoing kinetic energy, which is the mv sub 2. And the equation will be mv sub 1 squared over 2 is equals to shaft power plus mv sub 2 squared over 2. And the wind turbine efficiency will be wind turbine efficiency is equals to shaft power over mv sub 1 squared over 2. Combining the two equations above yields mv sub 2 squared over 2 is equals to mv sub 1 squared over 2 times 1 minus the wind turbine efficiency. And for the exit velocity, the formula is v sub 2 is equals to v sub 1 times the square root of 1 minus the wind turbine efficiency. This relation enables us to determine the exit velocity when the turbine efficiency is known and the frictional effects are neglected. Betz limit for wind turbine efficiency. The basic function of a wind turbine is to convert kinetic energy of air into work. And ideally, the wind turbine has efficiency of 100%. This conversion is perfect under the ideal conditions based on the second law of thermodynamics. The equation mv sub 1 squared over 2 equals shaft power plus mv sub 2 squared over 2 shows that this would be the case only if when the velocity of air at the turbine exit is zero. But this is not possible for operational reasons because the air must be taken away at the turbine exit to maintain the mass flow across the turbine. It turns out that there is a maximum possible efficiency for a wind turbine, and this was first calculated by Albert Betz in the mid-1920s. The figure shows that if we consider the two control volumes surrounding this area, a large control volume and a small control volume, with upstream wind speed V taken as V sub 1. The top and bottom streamline can be thought of as forming an imaginary duct for the flow of air through the turbine. Since locations 1 and 2 are far from the turbine, we take P sub 1 is equals to P sub 2 equals to P atmospheric, resulting no net pressure force on the control volume. We approximate the velocities at the inlet 1 and the outlet 2 to be uniform at V sub 1 and V sub 2 respectively, and the momentum flux correction factors to be unity. Then, the momentum equation for this simplified case can be written as F sub r is equals to m times V sub 2 minus V sub 1, where the F sub r is the reaction force on the turbine. The smaller control volume in the figure encloses the turbine. Since we approximate the turbine as a disk, the control volume is thin in the limit. Thus, A sub 3 is equals to A sub 4 is equals to A. Since the air is considered to be incompressible, then V sub 3 is equals to V sub 4. However, the wind turbine extracts energy from the air, causing a pressure drop. Thus, P sub 3 is not equal to P sub 4. When we apply the streamwise component of the control volume momentum equation on small control volume, we get F sub r plus P sub 3 times A minus P sub 4 times A is equals to 0. If we rearrange this, we get F sub r is equals to P sub 4 minus P sub 3 multiplied by A. Since it is extracting energy from the air, the Bernoulli equation is certainly not applicable across the turbine. However, it is a reasonable approximation between locations 1 and 3 and between locations 4 and 2. In this ideal analysis, the pressure starts at atmospheric pressure far upstream, P sub 1 is equals to P atmospheric, rises smoothly from P sub 1 to P sub 3, drops suddenly from P sub 3 to P sub 4 across the turbine disk, and then rises smoothly from P sub 4 to P sub 2, ending at atmospheric pressure far downstream of P sub 2 is equals to P atmospheric. We add the two equations setting P sub 1 is equals to P sub 2 is equals to P atmospheric and V sub 3 is equals to V sub 4. In addition, since the wind turbine is horizontally inclined, Z sub 1 is equals to Z sub 2 is equals to Z sub 3 and it equals to Z sub 4, or the gravitational effects are negligible in air anyway. After some algebra, this yields to V sub 1 squared minus V sub 2 squared over 2 is equals to P sub 3 minus P sub 4 over the density. Substituting M is equals to density V sub 3 times A into the equation above, and then combining the result with the equation we get yields V sub 3 is equals to V sub 1 plus V sub 2 over 2. Thus, we conclude that the average velocity of the air through an ideal wind turbine is the arithmetic average of the far upstream and far downstream velocities. Of course, the validity of this result is limited by the applicability of the Bernoulli equation. Next, figure shows the qualitative sketch of average streamwise velocity and pressure profiles to a wind turbine. For a convenience, we define a new variable A as the fractional loss of velocity from far upstream to the turbine disk, as A is equals to V sub 1 minus V sub 3 over V sub 1. The velocity through the turbine thus become V sub 3 is equals to V sub 1 times 1 minus A, and the mass flow rate through the turbine becomes M is equals to density V sub 3 times A is equals to density A times V sub 1 times 1 minus A. Combining this expression for V sub 3 with the equation, we will get V sub 2 is equals to V sub 1 times 1 minus 2A. For an ideal wind turbine without irreversible losses such as friction, the power generated by the turbine is simply the difference between the incoming and outgoing kinetic energies. Performing some algebra, we get ideal power is equals to M times V sub 1 squared minus V sub 2 squared over 2 is equals to density times A times V sub 1 times 1 minus A times V sub 1 squared minus V sub 1 squared times 1 minus 2A squared over 2 is equals to 2 density A times V sub 1 cubed fractional loss of velocity times 1 minus fractional loss of velocity squared. Assuming no irreversible losses again, and transferring power from the turbine to the turbine shaft, the efficiency of the wind turbine is expressed as wind turbine efficiency is equals to shaft power over 1/2 times density times V sub 1 cubed times area is equals to ideal power over 1/2 times density V sub 1 cubed times area is equals to 2 times density times area times V sub 1 cubed times fractional loss of velocity times 1 minus A, or the fractional loss of velocity squared, all over 1/2 times density times V sub 1 cubed times area is equals to 4 times the fractional loss of velocity multiplied by 1 minus the fractional loss of velocity squared. Since the fractional loss of velocity is 1, it is the trivial case or the no power generated. So we conclude that the fractional loss of velocity must equal to 1/3 for maximum possible power coefficient. Then, substituting the value of 1/3 into the equation, we get that the maximum wind turbine efficiency is equals to 0.5926. This value of the maximum wind turbine efficiency represents the maximum possible efficiency of any wind turbine, and it's known as the Betz limit. All wind turbines have a maximum achievable efficiency less than this due to irreversible losses, which have been ignored in this ideal analysis. Figure shows the wind turbine efficiency as a function of the ratio of turbine blade tip speed, or the V sub tip is equals to omega times R to wind speed for several types of wind turbines, whereas the omega is the angular velocity of the wind turbine blades and the R is the radius. The angular velocity of rotating machinery is typically expressed in RPM, or number of revolutions per minute, and denoted by n. Noting that the velocity is distance traveled per unit time and the angular distance traveled during each revolution is 2 pi, the angular velocity of a wind turbine is omega is equals to 2 pi n rod per minute, or omega is equals to 2 pi n over 60 rods per second. From the wind turbine efficiency, we see that ideal propeller-type wind turbine approaches the Betz limit as omega r over v approaches infinity. However, the power coefficient of real wind turbines reaches a maximum at some finite value of omega r over v and then drops beyond that. In practice, three primary effects lead to a maximum achievable power coefficient that is lower than the Betz limit. First, rotation of the wick behind the rotor, or swirl, finite number of rotor blades and their associated tip losses. Tip vortices are generated in the wake of rotor blades for the same reason they are generated on finite airplane wings, since both produce lift. Non-zero aerodynamic on the rotor blades, or the frictional drag as well as induced drag. In addition, mechanical losses due to shaft friction lead to even lower maximum achievable power coefficients. Other mechanical and electrical losses in the gearbox or the generator and etc. also reduce the overall wind turbine efficiency. As seen in the figure, the best wind turbine is the high-speed HAWT, and that is why you see this type of wind turbine being installed throughout the world. In summary, wind turbines provide a green alternative to fossil fuels, and as the price of fossil fuels rises, wind turbines will become more commonplace. Considerations in wind power applications. When a wind turbine project is underway on a windy site, many turbines are installed, and such sites are properly called as a wind farm or a wind park. Because of reduced site development cost, simplified transmission lines, and centralized access for operation and maintenance, the use of a wind farm is highly desirable. A wind turbine's application is off-grid homes, offshore areas, and demonstration projects. The following are the things need to consider in wind power application. First, the number of the wind turbine in a given location is determined by the distance between the turbines. If the turbines are too close to each other, the flow through one turbine affects the flow through the next turbine, reducing turbine performances. If the turbines are too far from each other, it indicates a poor use of the site because the potential for installing additional turbines for higher power outputs is not realized. As shown in the figure, there is an optimum spacing between the turbines, which is estimated to be 3 to 5 blade diameters between the turbines in a row, and 5 to 9 blades diameter between rows. The wind tower should be strong enough to support the weight of the turbine and withstand the forces generated by high wind speed and thrust on the wind turbine. The use of tall wind towers reduces turbulence and allows for greater seating flexibility. When planning a wind farm project on a specific site, several factors must be considered. Vegetation, topography, and ground roughness are all factors to consider. Other factors to consider include ease of access to the farm site, soil load capacity, and earthquake characteristics. Another important factor is to ensure that the proposed wind farm site is not a bird migration route. The number of offshore wind turbines has increased in recent years, particularly along the coast of Denmark, Sweden, and the Netherlands, as well as some other European countries. In Denmark, for example, an offshore wind farm has 91 turbines with a total capacity of 209 megawatts. It is important to choose the turbine blade diameter and power rating or generator size carefully in order to maximize power output from the turbine. When the diameter of the blade is increased at the same generator rating, the power curve shifts to the left, as shown in the figure. The rated power can then be achieved at a lower wind speed. The rated power increases when a larger generator is used. This is especially useful when the wind is blowing hard. As a result, if the turbine is mostly used at high wind speed, the generator size can be increased to maximize turbine power output. A reliable power grid or transmission network near the site and also good grid stability are required for effective wind power generation. The wind turbine produces power at 400 volts, which is then stepped up to 11 to 110 kilovolts. Poor grid stability may result in a 10% to 20% loss of power. Some wind turbines in China are not connected to the grid due mainly to stability issues. Wind turbine load factors typically ranges between 25 and 30%. That is, a wind turbine generates 25 to 30% of its rated power on average. The strength varies according to the time of the day. For example, in the early morning hours, power output is 80% of average power, while in the afternoon, power output is 120% of average power. Longer towers can help to reduce such fluctuations. An important reason for using tall wind towers is the wind speed increases with tower height, and higher wind velocities translate into higher power outputs. The wind speed can be expressed as functions of tower height and the roughness of the Earth's surface to be V is equals to V sub 0 is equals to H over H sub 0 raised to A, where V is the wind speed at height. V sub 0 is the nominal wind speed at height sub 0, and A is the friction coefficient of the ground. Typical values of friction coefficient are given in the table. Since the wind power is proportional to third power of wind speed, a slight increase in wind speed translates into a significant increase in power output. There is sometimes no connection to the electrical grid in the most remote parts of the world. Isolated power systems can be used in such places. Diesel engine power plants are commonly used for such autonomous power system because diesel system can be put into operation quickly and the units are small in comparison to other fossil fuel-based systems such as gas turbines and steam turbines. A hybrid power system consisting of a diesel system and a wind turbine system can be operated together in order to minimize diesel fuel consumption. In this operation, wind power should have priority in meeting electrical needs of the users and the diesel engines should be operated to meet the demand when wind power is not sufficient. A hybrid system for an autonomous power system can also integrate a diesel system with one or more of another renewable energy system such as wind, photovoltaic, or a hydropower system. The first wind turbine for electricity generation was developed at the end of 19th century. Two important technological developments took place after 1940. the introduction of three-blade structure and replacement of DC generator with AC generator. These were important in promoting the development of wind turbines. Wind turbine technology has advanced significantly over the years, but there is still room for advancement that will allow for greater adoption of this environmental friendly method of power generation. Some of the challenges in wind power technology are increasing the size of the wind turbine, designing the turbines specifically for a given site, developing new structural dynamic concepts, developing custom generations and power electronics, improving manufacturing technology, and better control strategy. The breakdown of capital cost of a wind turbine is given in the figure. The largest cost is due to gearbox brake and electrical system with contribution of 61%. Pitch, hub, and blade account for 27% of total capital cost. This is followed by tower system with 12%. There are other costs associated with turbine applications involving land, licensings, property tax, insurance, and labor, as well as operating and maintenance expenses. And that's all for wind energy. Thank you for listening.
Wind power potential. With the use of ideal turbines, we can directly and completely convert mechanical energy into mechanical work. The formula for mechanical energy is mechanical energy is equals to the mass flow rate multiplied to the sum of flow energy, kinetic energy, and potential energy. However, the inlet and outlet of a wind turbine are both equal to the atmospheric pressure and the elevation does not change. This results to a constant flow energy and potential energy. Therefore, we can safely remove the flow energy and the potential energy from the formula. We are now then left with the available wind power, expressed in available wind power is equals to 1 half mv squared, which is in unit of kilowatts. This is equivalent to the maximum power of a given velocity v. The mass flow rate is expressed as m is equals to rho av, which is in the unit kilograms per second, where rho is the density and a is the circular area of the blades. Substituting, we will get the available wind power is equals to 1 half rho av cube, which is the formula for wind power potential. Now, according to this formula, the power potential of a wind turbine is proportional to the cubic power of the wind velocity. Therefore, doubling the wind velocity will increase the power potential by a factor of 8. Now, let us prove this. Let's say that in a given location, the wind has a density of 1.2 kilograms per cubic meter at a velocity of 4 meters per second. If a wind turbine has a diameter of 1.03 meters, the maximum power it can generate can be determined by the available wind power formula. Substituting, we come up with the equation below, which equals to 32 kilowatts. After that, if you were to double the wind velocity from 4 to 8, we'll get 256 kilowatts. But why is this important? This is because one cannot simply put a wind turbine in the middle of nowhere without considering this power relation. Well, obviously, for practicality. The location, therefore, must have a steady wind velocity of at least 5 meters per second. But unfortunately, it does not end with just knowing the wind velocity at a given location. We must also consider factors such as blade diameter and the surrounding temperature during operation. The power potential is proportional to the density of air. Cold air has a higher wind power potential than warm air. Substituting the ideal gas relation, which is P is equals to rho RT, and the disk area equal to A is equals to pi d squared over 4, we substitute that into the original equation and we get the available wind power is equals to pi over 8 multiplied to pd squared v cubed all over RT. This states that the power potential is proportional to the square of the blade diameter. So therefore, doubling the diameter of the blade increases the power potential by a factor of 4. Let us solve a problem. A wind turbine with a blade diameter of 90 feet is to be installed in a location where average wind velocity is equals to 20 feet per second. The average temperature and pressure of ambient air in this location are 75 degrees Fahrenheit and 14.5 psia, respectively. Determine the wind power potential. Now, since we're given the gas constant of air, we can directly substitute it. By making use of ideal gas relation, we get the equation rho is equals to P over RT, and upon substitution, we get the answer 0.07317 pound mass per cubic feet. The blade span area is equals to A is equals to pi d squared over 4, which gives us 6,362 square feet. The mass flow rate is equals to m is equals to rho av, which gives us 9,310 kilograms per second. Now that we have all of this, we can now solve for the wind power potential, which is equals to 1 half mv squared. Upon solving, we get 78.5 kilowatts. However, we can directly solve for it using the formula pi over 8 is equals to pd squared v cubed all over rt. After substitution, we get 78.5 kilowatts, which is also the same result with the earlier solution, a much simpler and shorter way to solve the problem. Wind power density. For us to be able to compare two or more wind turbines and locations, it is important to consider available wind power per unit area, which we call the wind power density or our WPD. This can be expressed in WPD is equals to available wind power all over A, which is also equal to 1 half rho V cube. However, this is an instantaneous formula. Wind speed greatly varied from time to time throughout the year. Because of this, it's just logical to define the average power density based on hourly averages, expressed as the average WPD is equals to the average available wind power all over A, which is also equal to 1 half of rho of the average cube velocity. Here is the criteria for determining the site quality dependent on its average wind power density. Having less than 100 watts per square meter determines a poor site. Around a value of 400 watts per square meter determines a good site, and greater than 700 watts per square meter is a great site. Let us put that info in a real-life application. Here's an example. Consider two locations, location A and location B, with average wind power densities of 250 watts per square meter and 500 watts per square meter, respectively. Determine the average wind speed in each location. Take the density of air to be 1.18 kilograms per cubic meter. If a turbine with a diameter of 40 meters is to be installed in location A, and a turbine with a diameter of 20 meters is to be installed in location B, what is the ratio of wind power potentials in location A to location B? If we solve for the wind velocity at the two locations, we get 7.51 meters per second for A and 9.46 meters per second for B. Since the blade span area is proportional to the square of the diameter, we will be using the square of the diameter for substitution in the final formula. The wind power potential is proportional to the product of WPD and the square of the diameter. Making use of WPD and blade span area formula, we get 2. From this, we can conclude that the wind power potential in location A is twice the power potential in location B.